When an object moves in a straight line, we describe it using force, mass, and velocity. But what happens when things spin? From turning a doorknob to rolling wheels to spinning planets, rotation is everywhere in physics. While a motion looks different, the ideas behind it are surprisingly similar. In this video, we'll cover the physics of rotary motion, also known as rigid body rotation. You'll see how force turns into torque, how mass distribution affects motion, and how spinning objects store energy as rotational kinetic energy. We'll compare common rotating systems such as rings, solid disks, and spheres, and uncover why objects with the same mass can rotate differently. What's the difference between circular motion and rotary motion? The difference lies on the location of the axis of motion. In circular motion, an object moves along a circular path around a fixed point or axis outside of the object. An example would be a satellite circling a planet, while rotary motion involves an object spinning about an internal axis and passes through the object. So I have an object here, and we have an axis going through it, and it's spinning around that axis. The object does not move in a circular path around an internal axis, so think of something like a top spinning on its axis. So I have an object spinning. We're going to let theta be the angular displacement. R will represent the radius of the object. S will represent the length of the arc. So we can say that it's going to be the length of the arc divided by the radius. So we're going to say that theta is going to equal S over R. Oftentimes we'll say that S is equal to theta times R. And let's go ahead and save this here because this is important. We'll be using this in the future. Okay, you know that one revolution is equal to 360 degrees. It's also equal to 2 pi radians. Radian will be the preferred unit in physics because the relationship between angles and arc length fit well into what we're trying to do with physics. Angular velocity, we'll use a W or the omega symbol to represent angular velocity. It's going to equal the change in angular displacement over the change in time. So that's an important formula we need to remember. Okay, tangential velocity, or the linear velocity at any instant along the circle. So if I were to draw a circle here, a radius r, this velocity here will be the tangential velocity. And we have the angular velocity here. We're going to say that the velocity along the tangent is equal to the angular velocity times the radius. Angular acceleration will be the change in angular velocity over the change in time. And we're going to use the alpha symbol. It's going to equal the change in angular velocity over the change in time. This is going to be measured in radians per second squared. Let's go ahead and add these units up here. Be radians per second, meters per second, and radians per second squared. We think of velocity as a change in arc over time. Okay, so we're going to say then that velocity is equal to 2 pi r over t, measured in meters per second. We can also say that velocity is equal to the angular velocity times the radius. For acceleration, we said that acceleration equal to the change in angular velocity over the change in time. So that means we could say that acceleration is equal to velocity over time times the radius. Now, velocity over time is linear acceleration. So I can say then that acceleration is equal to linear acceleration divided by the radius. This is an important formula. Oftentimes you'll see it written as acceleration is equal to, my kids call this acceleration equals fish times r. That's what my kids always call this. Rotational inertia, we represent with the letter I, is the resistance of a rotary object to the change in angular velocity. So if I have 2 meter sticks here, all right, and I tape a 500-gram weight to each meter stick, I secure the bottom so they can rotate. If I release them at the same time, at the same angle, and let them rotate to the floor, which one will hit the ground first, or will they hit the ground at the same time? The first meter stick, most of the mass is on the outer portion. On the second one, the center of mass is in the center. Well, depending upon where the center of mass is, determines at which rate or what rate that they will rotate at. We need to talk about rotational inertia. For example, I have a ring. For a ring, I equals mr squared. Most of the mass of the ring is on this outside. All right, if I have a disk, okay, I is equal to 1/2 mr squared. A disk has an even distribution of mass. And if I have a sphere, that's going to equal 2/5 mr squared. So if I were to release these and they travel down the ramp, which one will finish first? The one with the smallest rotational inertia will make it to the finish line first, and the one with the largest will come in last. So the sphere will come in first, the disk will come in second, and the ring will come in last. To calculate the velocity of a ring going down an inclined plane, we can say that its potential energy at the top is equal to its kinetic energy in a linear direction plus the kinetic energy while rotating. All right, so kinetic energy linear is equal to 1/2 mass times velocity squared. Kinetic energy of rotation is equal to 1/2 I omega squared. So we can say here then that potential energy at top is mass times gravity times height. It's equal to 1/2 mass times linear velocity squared plus 1/2 I omega squared. Okay, let's expand this a little bit. So this is mgh equals 1/2 mb squared plus, okay, for a ring, we said that I was equal to mr squared. And I'm going to substitute V over R for omega. So it'd be velocity squared over radius squared. Okay, so I see that this radius cancels this radius. I also see that mass cancels mass cancels mass. So I can say that G times H 1/2 V squared plus 1/2 V squared. So G over H equals V squared. So V is going to equal the square root of gravity times the height. So this is the velocity for a ring rolling down an inclined plane. Let's derive the formula for a disk rolling down an inclined plane. Potential energy at the top is equal to the kinetic energy linear plus the kinetic energy for rotation. Mass times gravity times height equals 1/2 mass times velocity squared. So this is 1/2 I omega squared. This will be 1/2 of, okay, we said that for a disk it is 1/2 mr squared. And again, we're going to substitute V squared over R squared for omega squared. R squares cancel. Masses cancel. So G times H equals 1/2 V squared plus 1/4 V squared. Common denominator is 4. That's 2/4 plus 1/4. That gives me 3/4 V squared. So I can say then that V squared is to taking the 3/4 to the other side. I have to flip it so it'll be 4/3 GH. The velocity for a disk will be the square root of 4/3 GH. Now let's derive the equation for the velocity of a sphere going down an inclined plane. So potential energy at the top is equal to kinetic energy linear plus kinetic energy rotational. mgh equals 1/2 mass times velocity squared plus 1/2 I omega squared. Okay, so I here is 2/5 mr squared, and omega squared is v squared over r squared. R's cancel. Mass cancels mass cancels mass. So I have 1/2 v squared plus 2/10 v squared. Okay, the common denominator will be 10. GH is equal to 5/10 v squared plus 2/10 v squared. So G over H is equal to 7/10 v squared. Take my 7/10 over to the other side so that v squared will be equal to 10/7 GH. So velocity is equal to the square root of 10/7 GH. So there we have the equations for a ring, thin ring, a disk, and a sphere rotating down an inclined plane. Torque is equal to the force being applied times the radius or distance times sine theta. So this force in newtons, radius or distance in meters. We can also say that torque is equal to the angular acceleration times the moment of inertia. So when you have a steering wheel, for example, you're applying torque or force over a certain radius. If the radius increases, the torque increases. Think of a crank. If I have a crank here, and I'm turning this crank like a pencil sharpener or a crank on a winch or whatever. This is an example of torque, where this is the radius. I apply my force here. If I have a bolt and I take a wrench and I turn the bolt with a wrench, this is the radius. The longer the wrench is, the more torque you have, because your force is applied over a greater distance. Lastly, let's compare some linear equations to some rotary equations. Remember, earlier we said that the final velocity for an object is equal to the initial velocity plus acceleration times change in time. Well, for rotary, the final is equal to the initial plus acceleration times change in time. Earlier we said that distance, the change in distance, is equal to the initial velocity times change in time plus 1/2 acceleration change in time squared. Here we can say the change in theta is equal to the initial angular velocity change in time plus 1/2 acceleration change in time squared. We also said the final velocity is equal to the square root of the initial velocity squared plus 2a change in distance. The change in angular velocity is equal to the square root of the initial angular velocity squared plus 2 times acceleration times the change in theta. All right, so we can use these very similarly. So therefore, it shows that linear formulas and rotary formulas are basically the same thing with just a different perspective or point of view. A 300-gram uniform sphere, 12-centimeter radius, spins 8.2 revolutions per second on an axis through its center. What is its rotational kinetic energy? So kinetic energy for rotation is equal to 1/2 I omega squared. Remember now that I is for a sphere is equal to 2/5 mr squared. And we can't work with revolutions per second. We have to be in radians per second. So to get that, I need to convert my 8.2 revolutions per second into radians per second. So I'm going to multiply this times 2 pi radians per 1 revolution. So that's going to give me 51.5. Let me write that a little plainer. That'd be radians per second. So we will say 1/2 I, which is 2/5 mr squared, times w squared. And so our w will be 51.5. It is squared because it's squared in a formula. This will be 1/2 times 2/5. Okay, the mass is 3.3 kilograms. The radius is 0.12 meters squared. times 51.5 squared. So this would be 2/10. If I multiply this out, it would give me 0.3 times 0.0144 times 2652.25. I plug all this in my calculator, so I get my kinetic energy of rotation is equal to 2.3 joules. A solid ball is rotated by applying a force of 4.7 newtons tangentially to it. The ball has a radius of 14 centimeters and a mass of 4 kilograms. What's the angular acceleration of the ball? So torque is equal to acceleration times moment of inertia. Torque is also equal to force times radius or distance. I'll set those equal to each other. I want to isolate acceleration, so I'm going to divide both sides by I. Okay, so now we can plug into our data. So acceleration is equal to a force of 4.7 newtons. The radius here is 0.14 meters. I had to move a decimal 2 places over. I will be 2/5. That'd be mr squared. So the mass is 4, and the radius is 0.14 squared. So my acceleration will be equal to 21 radians per second squared. The outer edge of a truck tire that has a radius of 45 centimeters has a velocity of 26 meters per second. What's the angular velocity of the tire in radians per second? All right, so I have a tire. Its radius is 0.45 meters. It has a velocity of 26 meters per second. And rotation is equal to velocity divided by the radius. So it's going to be 26 meters per second divided by 0.45 meters. That would give me 57.7 repeating radians per second. Okay, a ball rotates at 12.5 revolutions per minute. If the ball has a radius of 6.25 centimeters, what is the velocity of a point along the ball's equator? Let's convert this 12.5 revolutions per minute into radians per second. So 2 pi radians is 1 revolution. And 1 minute is 60 seconds. This will give me 1.31 radians per second. Now, velocity is equal to omega r. So it's going to be 1.31 times the radius of 0.0625. So velocity will be 0.082 meters per second. A basketball is rolled 12 meters down the court. A regulation basketball has a diameter of 24.1 centimeters, a mass of 0.6 kilograms, and a moment of inertia of 5.8 times 10 to the negative third kilogram meter square. The basketball's initial velocity is 2.5 meters per second. The velocity is equal to omega r. So omega then is equal to velocity over r. So it's going to be going 2.5 meters per second. And my radius is 0.241 halves, which is half the diameter. So this is 20.75 radians per second. That will be its angular velocity. This problem is the same as the last problem, except this time let's solve for how many revolutions does the basketball make. So it travels 12 meters. I'm going to say that theta is equal to this arc over its radius. So it's traveled 12 meters, and its radius is 0.241 halves. It gives me 99.59 radians. So 99.59 radians times 1 revolution over 2 pi radians. This will give me 15.8 revolutions. A bicyclist of mass 65 kilograms stands on the pedal of a bicycle. The crank, which is 0.17 meters long, makes an angle of 45 degrees with the vertical. The crank is attached to the chain sprocket, which has a radius of 9.70 centimeters. What force must the chain exert to keep the sprocket wheel from turning? So if this is the sprocket, I have a pedal coming up here. This pedal is 45 degrees. This radius is 9.7 centimeters. He's applying a force here of 65 kilograms to give me force. So remember that force equals mass times gravity. So that means this is 65 times 9.8. So he's applying a force of 637 newtons. All right, the chain is coming off here like this. All right, so I'm going to call this the sprocket. Call this the chain. This is the pedal. I'm going to say that the torque exerted by the sprocket must equal the torque by the pedal. So we're going to say that this is force times the radius of the sprocket is equal to the force of the pedal times the radius of the pedal times the sine of theta. All right, so the force of the sprocket times 0.097 is going to equal the force, which is 637, times its radius, which is 0.17, times the sine of 45. Okay, so the force due to the sprocket, I'm going to divide both sides by the 0.097. So his force is 789.4 newtons. That's the resistive force of the sprocket, so the chain doesn't move. Determine the constant torque that must be applied to a 50 kilogram flywheel with a radius of 40 centimeters to give it an angular speed of 300 revolutions per minute in 10 seconds. Flywheel is essentially a thin ring where all its mass pretty much is on the outside, or the majority of its mass. And with thin ring, remember that I equals mr squared. All right, we need to find our angular velocity. So let's take our 300 revolutions per minute. Let's convert that into radians per second. So 1 revolution is 2 pi radians. 1 minute is 60 seconds. That will give me 31.42 radians per second for my angular velocity. So torque is equal to the acceleration times the moment of inertia. So the torque is going to equal the change in angular velocity over the change in time times mr squared. So we're going to say then that torque is going to equal my angular velocity is 31.42 rads per second over 10. My mass is 50 kilograms. And my radius is 0.4 square. So my torque is going to be equal to 25.1 Newton meters. Rotary motion follows the same physics as linear motion, just in a rotating form. Once you understand torque, moment of inertia, and rotational kinetic energy, you can analyze how any rigid body spins, rolls, or rotates. Please like and subscribe to the video. I'll see you soon with another educational tutorial. Thank you very much. Goodbye.